Okay, so we'll discuss about Maxwell's speed distribution of gaseous molecules. Okay, so let us consider a gas. Consider a gas containing n molecules. Okay, let us assume that the gas contains n molecules. Then you know very well, in gaseous state, molecules are not static, correct? They keep on move randomly. So due to random motion, and the molecule also undergo collision, isn't it? So molecules, gas molecules, okay, they move in a random and chaotic manner. Okay, they move in random and chaotic manner, and they undergo collision. You know very well, right? Molecules undergo collision. Okay, so collision occurs between molecules. Okay, so what will happen because of the collision? The velocities of the molecules keep changing with time. Keep changing with time. As the time progresses, okay, the velocity of the molecule keep on changing. Right? So at a particular instant, some molecules may have very low velocity, some molecules may have very high velocity. Right? So velocity is distributed. Isn't it? So gas molecules, not all gas molecules have same velocity. This is very important. Take note. Listen carefully. Not all gas molecules have same velocity. Okay, at a given time. Okay, at a particular time, right? All molecules do not have same velocity. Actually, velocity is distributed. Right? So actually, velocity, right, is distributed. Velocity is distributed, which means some molecules have very low velocity, some molecules have high velocity, some molecules have medium velocity. So in gaseous state, or the molecules in the gaseous state, okay, they move with different velocities. Okay, to handle this problem, Maxwell and Boltzmann, they utilized the statistical idea, and they derived an expression for probability or fraction of molecule having a particular velocity. Okay, let me write in the next page. Just copy on this. So, using statistical approach, using statistical mechanics, Maxwell and Boltzmann, they gave an expression to find the probability of finding a molecule with velocity u. Okay, so first I'll write the formula. Listen, what is the probability of finding molecules with the velocity range from u to u plus du. Observe carefully. See, this is actually the technical term that we use. What is the velocity, or what is the probability of finding molecule in the velocity range u and u plus du, where du should be very, very small. Okay, say suppose some molecule move with velocity, say for example 10 meter per second. Some molecule move with velocity 10 meter per second. And some molecules move with velocity say 10 plus 2 meter per second. Just for understanding purpose I'm writing. 10 plus 2 means 12, right? So between 10 meter per second and 12 meter per second, how many molecules are there? What is the probability? So probability of finding molecules with the velocity range from u and u plus du is given as, is it P of u du, right? Probability of finding molecule in the small range du is equal to, and this is the derived formula. I am not going to derive, but I am going to give you the final expression, right? Okay, before that, this is also equal to dnu by capital M. What is dnu? It is the number of molecules, okay, having a number of molecules present in the range u plus du, and this is total number of molecules. I repeat, what is dnu here? dnu is nothing but number of molecules having velocity in the range u and u plus du. In this range, how many molecules are there? That is dnu. So this is number of molecules in the range at du divided by n. N is the total number of molecules. Will give you fraction of molecule having velocity are present in the velocity u and u plus du, are present between u and u plus du. Okay. Now observe carefully. Maxwell and Boltzmann derived an expression for this. Let me write the expression here. That is probability of finding the molecule within this velocity du, within the small velocity range du, is given as 4 pi into m by 2 pi kbt whole power 3 by 2 into u square and e power minus m u square by 2 kbt, right, into du. So this formula will give you the probability of finding molecule in the range u and u plus du, which means in the range du. In the range du, how many, what is the probability of finding the molecules? Right? In this speed velocity range, okay, what is the probability of finding molecule? So this formula will give you that. Remember, I am using symbol u for velocity. In some book, you may see velocity will be represented as v. In some book, it is given as u. Some people also use the symbol c for velocity. Okay. So you can take any symbol, but I am going to use the symbol u for velocity of molecules. Right. Now, here, m is nothing but mass of one molecule. Kb is Boltzmann constant, T is temperature. Here I have square of the velocity. E power minus m is mass of the one molecule. U square 2 Kb is Boltzmann constant, T is temperature. This is the expression which gives you probability of finding molecule in the velocity range u and u plus du. Okay, take note. Listen, now what I am going to do, I am going to remove this du both sides. So what we get is P of u is equal to 4 pi m by 2 pi kbt whole power 3 by 2 into u square into e power minus m u square by 2 kbt. Okay, yes, this will give me probability of finding molecule with the velocity u for a specific velocity, for a particular velocity u. How many molecules, or what is the probability of finding molecule? Probability of finding molecule having velocity u. Okay, yes, you will get that answer if you know this value. Okay, this is equal, this probability is equal to this. Okay, take it. Yeah. So if I plot this probability, that is probability of finding molecule with velocity u versus velocity of the molecule, how the graph will look like. Observe carefully, I am plotting probability. Probability is nothing but fraction. See? Remember, I told you this, P of u into du is equal to dnu by n, correct? I can also write this as P of u is equal to 1 by n into dnu by du. Okay, so this will give me, right, how number of molecules, right, number of molecules having a particular velocity u divided by total number will give me the fraction of molecule having velocity u. So remember, this is also equal to, this probability is also equal to fraction of molecule having velocity u. Correct. So if I plot this versus velocity, what will happen? See this graph, see this equation. Here 4 pi m, these are all constant quantities. So I have u here and u here. Okay, as u increases, listen, first this function becomes dominant. And this function, okay, is insignificant, okay, for lower velocities. Therefore, P of u increases, right, as u increases initially. So it increases like a parabola. U square, no. So it increases like a parabola. Then, after sufficient velocity, then the exponential term becomes dominant. Compared to this, I have minus here, therefore it will decrease exponentially. It decreases exponentially like this. We'll get a graph like this. Okay? So what does this graph tells you? Listen, for this velocity, suppose I take some velocity u1. For this velocity, yes, we have some fraction of molecule. So this fraction of molecule have velocity u1 at a particular temperature. And I'll take another velocity u2, draw a straight line. Listen, this fraction of molecule here, this fraction of molecule have velocity u2. Like that, we have different fractions of molecules having different velocity. So velocity is distributed like this. Now, see here, there is a point. Observe carefully. There is a point. There is a velocity. Okay, some velocity here. This velocity. At this velocity, listen, maximum number of molecules or maximum fraction of molecule have this velocity called the most probable velocity, UMP. What is UMP? It is the velocity possessed by maximum number of molecule or maximum fraction of molecule, you can say like that. Is this clear to all? So how to find the most probable velocity? Very easy. You know very well, at this tip, this is actually a peak, right? This appears like a peak. At this tip, first derivative value is 0. You know very well, you might have heard about maxima, minima. At the maximum, first derivative value is 0. So what should I do? Listen, I have to differentiate this P of u with respect to velocity. See, I am going to differentiate this P of u with respect to velocity, dy by dx, dy by dx I am doing. Okay, and put that value equal to 0. Okay, this is the condition for maximum. Condition for maximum. So I'll keep this d by du as such. Now what is P of u? P of u is equal to 4 pi into m by 2 pi kbt whole power 3 by 2. Then we have u square e power minus m u square by 2 kbt. Okay, yes, this is P of u. That should be equal to 0. Okay, take down. Okay, I'll remove these common terms. That is 4 pi constant terms, 4 pi m by 2 by kbt whole power 3 by 2. These are all constant terms. I'll bring it out. If I bring it out, those terms exist as multiplicative term. And if I bring it to the right hand side, 0 by something is 0 only. So simply remove these terms. Okay, so what we get is d by d is equal to u square into e power minus m u square by 2 kbt. This is the term that remains. Now we have to differentiate. I have u here, I have u here. So you have to use UV method. What is UV method? First keep u as such. There is this term as such. Differentiate this. If you differentiate exponential term, you will get the same term first. Then differentiate the power. If you differentiate the power, see u square, if you differentiate, you get 2mu. This 2 and this 2 cancel. So what we get is minus mu by kb into t. We get this. Plus, what is the second term? Keep exponential as such. Keep the exponential term as such and differentiate u square. If you differentiate u square, you get 2u equal to 0. Now I can take this exponential term as common. I can also take u also as common. So what we get is bring all the term this side and bring it to the right hand side, it becomes 0. Okay, so what we left with is u into minus, I took this u constant, right? So we have one more u here. So u square, alright, let it write once, u mu by kbt. Here we have plus 2 equal to 0, right? Or bring this 2 to the right hand side. So what we get is, or bring this quantity to the right hand side. So 2 is equal to mu square by kbt. Okay, and multiply this by kbt here and divided by m. So u square equal to 2 kbt by m, or u is equal to square root of 2 kbt by m. This is nothing but the most probable velocity. So most probable velocity is equal to square root of 2 kbt by m. Here m is the mass of one molecule. If I put molar mass, what will happen? See here, we know very well, kb. What is kb? kb is nothing but gas constant by Avogadro number. So in the place of kb, if I substitute this, we get 2 RT by m into Avogadro number. M is mass of one molecule into Avogadro number will give molar mass. So this is equal to square root of 2 RT by capital M. This is what we call as most probable velocity. Take the note. What is the formula for most probable velocity? UMP equal to square root of 2 RT by M. R is gas constant, T is temperature, M is molar mass. M is molar mass. Okay. What is the formula for average velocity? Average velocity. How to find average velocity? Listen, in probability, we have a formula to calculate average. Okay. Yes. What is it? Average of any value x is equal to integral. Okay, integral you have to do all over space, right? Integral the value x into probability of finding that x into dx. This will give me the average. This is average formula. Okay, people use in mathematics. Okay, if probability is available, you can use this formula to calculate average. Now, what is the average velocity? I am going to use the same formula. Average velocity is equal to integral. Listen, some molecule may have zero velocity. Some molecules may have very high velocity, say infinity. So velocity is distributed from 0 to infinity. Just assume like that. Then to get the average, multiply in the place of x, you put u into p of u into du. We see, I have given the formula for p of u. Substitute the p of u and do the integration. You will get the final expression, but I am not going to do that. The average velocity comes out as, after simplification, it comes out as square root of 8 RT by pi into take. In similar manner, anyone tell me how to find average of the square velocity? Now I want to calculate average of the square velocity. Can anyone suggest me some idea? Yes. Yes.
830 by m, sir.
No. This is average velocity. Square root of 8RT by pi into. Correct. Now I am asking average of the square velocity. Yes.
Sorry, x squared into pu squared, sir.
That's all. Integral 0 to infinity u square into p of u into du. That's all. Right? In this place you put u square. That's all. And if you simplify this integration, you will get the answer as 3RT by m. Okay, take note. Now what I am going to do, see, listen, suppose I have a gas which contain n molecules, okay. At a particular time or at a particular instant, let us say n1 molecules have velocity u1, n2 molecules have velocity u2. So I have many molecules like that. Okay, right? If I add all these things, n1 plus n2 plus n3, I will get the total n. Right? So, what is the average velocity? See, this number of molecules have velocity u1, this number of molecules have velocity u2, then this number of molecules, n3 molecule have velocity u3. Like that, different number of molecules have different velocities. Now, what is average velocity? Average velocity is equal to
summation.
Yes. Average velocity equal to, yes, how to do?
Summation of ui plus.
So, average velocity is nothing but this is u1 is the velocity possessed by n1 molecules. Or, okay, see, I'm sorry, I made a mistake. So, I have a gas with n molecule. At a particular instant, I made a mistake. See, molecule 1 have some velocity u1. And molecule 2 have velocity u2 at a particular instant. And molecule 3 have some velocity u3. Then molecule n, since we have totally n molecules, and molecule n have some velocity, say un, at a particular instant of time. Listen, I have told you, because of collision, the molecule 1, it has some velocity u1 at a particular instant. In the next instant of time, it will change. Okay, so at a particular instant, this is the velocity of molecule 1, this is the velocity of molecule 2, this is the velocity of molecule 3, and this is the velocity of molecule n. What is the average velocity? Add all the velocities u1 plus u2 plus u3 plus etc. plus un. Add all the velocities of all the molecules divided by add the number of molecules. So what is the total number of molecules? n. This is nothing but the average velocity, which we found that is equal to square root of 8RT by pi into m. Right? So if you know the temperature and the molar mass of the molecule, yes, we can find the average velocity directly. But this formula is applicable only for ideal gas. Keep that in mind. Okay, then second one. This is average velocity.
Sir?
Yes.
Sir?
So this is the meaning for average velocity. Then what about average of the square velocity? See, this symbol, okay, we use this symbol for average. So this is average of square velocity. What is average of square velocity? Simple. Listen, at a particular instant, molecule 1 has some velocity u1. Molecule 2 has some velocity u2. Okay. Now you take the squares of this. Square of the velocity u1 plus square of the velocity u2 plus square of the velocity u3. So like that, you take the square of all the velocities and divide this value by total number of molecules. This will give you average of the square velocity, which is equal to which is equal to 3RT by m. I gave that. Okay. This is equal to 3RT by m. This is average of the square velocity. Now, I will define another velocity. This is very important. Listen. This is called URMS. What is URMS? Root mean means average. Root mean square velocity. Root mean square velocity. What is that? It's nothing but, see, take the root, mean means average, square velocity is this, right? So take u1 square plus u2 square plus etc. plus un square by n. This will give me the average of the square velocity, and take the square root, you'll get root mean square velocity. Okay, listen, this is nothing but, see, I'll keep the square root as such. The content present inside the square root, which is nothing but average of the square velocity. Okay, so root mean square velocity is equal to, anyone tell me? What is the average of the square velocity? Average of the square velocity is 3RT by m. In the place of average of square velocity, you put 3RT by m, you will get URMS. So what is URMS?
3RT by m.
That's all. Root mean square velocity equal to square root of 3RT by m. Take note. This is root mean square velocity. Listen. So this is very, very important. We have derived a few formulas. Listen, most probable velocity is equal to square root of 2RT by m. Number 2, URMS, root to mean square velocity, it is actually equal to square root of average of the square velocity, which is nothing but square root of 3RT by m. Then I gave another velocity called average velocity, right? U average. Average velocity is equal to square root of 8RT by pi into m. Okay, these are the three important velocities, okay, which is connected with the gaseous state. Right? Try to remember all these things, right? Take them. Listen, I am going to compare these velocities. Right? In all these, listen, RT by m is common. Correct? Here I have RT by m, here I have RT by m, here also I have RT by m. Now, we have to compare square root of 2 here, square root of 3 here, and square root of 8 by pi here. Among the three, which one is larger? Okay, among the three, most probable velocity has the lowest value. Next is average velocity. Okay, let me write like this. Instead of putting this symbol, I'll put like this. U average means average velocity. Then next is URMS. URMS is the highest, right, at a particular temperature. At a particular temperature of an ideal gas. Remember, this formula is applicable only for ideal gas. Okay, take it. I'll do some manipulations here. See, I'll take URMS, root to mean square velocity, which is nothing but square root of 3RT by m, right? Now, what I'm going to do, I'll take this root 3 as such, right? I'll multiply the numerator and denominator by root 2. See what I'm doing? I'm dividing this by root 2 and I'm multiplying by root 2. And we have square root of RT by m. Okay? So, URMS equal to, observe carefully, I can combine this, I can write root of 3 by 2. I'll bring this root 2 inside, so you'll get 2 inside, so I can write 2RT by m. Okay? What is square root of 2RT by m?
Most probable.
Most probable. So what is URMS then? URMS equal to square root of 3 by 2 into UMP. This is the relation between URMS and UMP at a given temperature T. Right? About kinetic theory of gases. Right? You might have heard about kinetic theory of gases. And this theory is also, it is applicable only for ideal gas. And in kinetic theory, there is an equation PV is equal to 1 by 3 m n u RMS square. We have an equation. It's called kinetic theory equation. P is the pressure of the gas, V is volume of the gas, 1 by 3, m is mass of one molecule, n is number of molecule. It is not number of mole. Here n is number of molecules. URMS, you know, root mean square velocity, and we have square of URMS. Square of URMS. Okay. Now listen carefully. In lower classes, people will use this formula to find the root mean square velocity and other velocities and all. To find root mean velocity specifically. Okay. Yes. Listen. I have told you this formula is applicable only for ideal gas. Suppose I'll take 1 mole of ideal gas. 1 mole of ideal gas. Suppose I'll take 1 mole of ideal gas. For 1 mole of ideal gas, you know very well PV is equal to RT. This is ideal gas equation. For 1 mole, PV is equal to RT. So in the place of PV, I'll put RT. So we get RT is equal to 1 by 3 into M is mass of 1 molecule. Now we have taken 1 mole of gas. So total number of molecule is nothing but Avogadro number. So see here, N is number of molecules in the gas. Right? We have taken 1 mole. 1 mole means it contains Avogadro number of molecules. So in the place of small n, I'll put Avogadro number into URMS square. Okay. What is M into Avogadro number? M is mass of 1 molecule into Avogadro number will give
Molar mass.
Molar mass. Bring this 3 this side. So we'll get 3 RT into molar mass into URMS square. Bring this M here. So what is URMS? Anyone tell me? What is URMS?
Root 3 RT by
Square root of 3 RT by M. We get the same formula. We get the same formula. Okay. Yes. Take. Because this equation also derived from Maxwell's distribution. This equation also derived from Maxwell's equation. That's why we get the same result. Right? Then in kinetic theory of gases, right, molecules are assumed to be hard spheres. Meaning the molecule may have tetrahedral structure or octahedral structure. Don't worry about the full structure of the molecule. Assume the molecule as a hard sphere. That's all. If we assume like this, then the entire energy, right, exists as translational energy. So molecules possess only translational kinetic energy. Since there is no attraction or repulsion, potential energy also 0. V equal to 0 here. Remember. See, because we have taken ideal gas. In the case of ideal gas, there is no attraction or repulsion. So potential energy is 0. Therefore, the only energy which is available is translational kinetic energy. Okay. Now listen carefully. So what is the kinetic theory equation? KTG equation. KTG equation is PV equal to 1 by 3 M N U RMS square. Okay, this is the KTG equation. Now, what I am going to do, observe this carefully. I'll take okay, let me make some simplification here. I'll bring the 3 this side. So 3 into PV equal to, right? I'll divide both sides by 2. I'll divide this by 2 and this also by 2. So 1 by 2 M N U R M S square. Okay. Now listen. Half M U R M S square. What is this quantity called? Half M U square. Anyone?
Kinetic energy, sir.
M is mass of 1 molecule and this is square of the velocity. That is average kinetic energy, correct? It gives some average kinetic energy. So 3 by 2 into PV equal to, right, average kinetic energy. I'll put this symbol for average. This bar symbol also used for average. and the small subscript E represent average energy for one molecule. Average kinetic energy for one molecule into, I have N here. N is total number of molecules. Okay, suppose if I take ideal gas, see, 1 mole of ideal gas. Suppose I take for 1 mole of ideal gas, PV equal to RT, correct? So I'll put in the place of PV, I'll put RT. So what we get is 3 by 2 into RT into average equal to average kinetic energy per molecule into, since you have taken 1 mole of gas, N number of molecules is nothing but Avogadro number. If you bring this Avogadro number here, R by Avogadro number is Boltzmann constant. So what we get is average kinetic energy per molecule is equal to 3 by 2 kB into T. This is average translational kinetic energy per molecule. Listen, 3 by 2 is a constant, kB is a constant. So average kinetic energy depends only on temperature. Okay, it does not depend on any other quantities. It depends only on temperature. Okay, this is average kinetic energy per molecule for one molecule. Right? Now, what is the average kinetic energy for 1 mole of molecule, 1 mole of gas? Right? For 1 mole, what we have to do? We have to multiply this by Avogadro number. Right? Kb into Avogadro number will become R. So, let me write the next page. So, what is the average kinetic energy? Now I am using capital E because this is not for 1 molecule, this is for 1 mole of gas. Average kinetic energy per mole of gas, per mole is equal to, okay, listen what we should do, multiply this by Avogadro number. This is for average kinetic energy for 1 molecule. If I multiply this by Avogadro number, I will get average kinetic energy for 1 mole. Correct. So Avogadro number into kB is R. So we get 3 by 2 RT. 3 by 2. This is average kinetic energy per mole. For N mole, average kinetic energy for N mole of gas. Suppose if I take N mole, then I will get 3 by 2 nRT. This is the average kinetic energy for N mole of gas. Okay.